Suppose we want to multiply the real number 2 by the complex number 1 plus 3i. Here is 1 plus 3i on an Argand diagram. The real part is 1, the imaginary part is plus 3. Now multiplying by 2 has the effect of changing r, where r is the modulus of the complex number. So that was discussed in the previous video. What happens is we just double r. So 1 plus 3i becomes 2 plus 6i. But we don't affect theta, where theta is this angle here. So here's the picture. We just double the x, our real value of the complex number, and double the y, our imaginary value of the complex number. So the modulus of 2 plus 6i is actually 2 times the modulus of 1 plus 3i. The modulus of 1 plus 3i is the square root of 1 squared plus 3 squared. That's the square root of 1 plus 9, or the square root of 10. So you can see that theta is left unchanged. When we multiply a complex number by a real number, we just scale that complex number. We could scale it up or scale it down, depending on whether this number is less than 1 or greater than 1. If this number was, say, a half, then we would scale down our complex number to a complex number with a smaller r value, with a smaller modulus. If this number here was, say, negative, then we would switch the direction of our complex number. You could think of our complex number as a vector, and we would switch its direction. So we would get this complex number down here, which is minus 2 minus 6i, if this number was, say, minus 2. Now here is an interesting question. What happens when we multiply a complex number by I? Well, we can just do the algebra here. I times 1 is I times 3i is 3i squared. We know that I squared is minus 1, so we have plus 3 by minus 1, which is minus 3. I'll write the real part first. The imaginary part is plus 1i. So let's plot that number. So we go to minus 3 on the imaginary axis, which is over here somewhere. And we go to plus 1 on... Sorry, we go to minus 3 on the real axis, and we go to plus 1 on the imaginary axis, which is about here. So we get this number here. This number is minus 3 plus 1i. What has actually happened here is that we have rotated our complex number anti-clockwise about the origin through an angle of 90 degrees. The r value has not changed actually. So r is the modulus of 1 plus 3i, which is the square root of 1 squared plus 3 squared. That's just Pythagoras' theorem. We just get this right angle triangle with sides of 1 and 3, and the hypotenuse is the square root of 1 squared plus 3 squared, or the square root of 10. And this hasn't changed. This distance here is also the square root of 10. So you see that multiplying by I rotates our complex number. So theta is affected, but r is not. R stays the same. The modulus stays the same. But theta for 1 plus 3i is this angle here. And theta for minus 3 plus I is this angle here. Again, you see theta is measured anti-clockwise from the positive real axis. So the difference in both of these angles is 90 degrees. By the way, this angle here is often referred to as the argument of the complex number, or ARG for short. So the argument of 1 plus 3i, as you can see, is an acute angle. That is an angle between 0 and 90 degrees. However, if we look at this angle here, we see that it's the argument of this complex number, which is minus 3 plus I, but it's equal to the argument of 1 plus 3i plus 90 degrees. Now, I could also have considered multiplying 1 plus 3i by minus I, and that will actually rotate the complex number 1 plus 3i clockwise about the origin. So we'll end up getting this complex number here, which is 3 minus I. So when we multiply by minus I, we rotate 90 degrees clockwise about the origin. Notice that we haven't scaled up R. R remains the same for all these vectors. Of course, if I'd multiplied by 2I, then we would not only rotate our complex number by 90 degrees about the origin, but we'd also multiply its length by 2. Now let's consider the multiplication of the complex numbers 5 plus 2i by 1 plus 3i. I've plotted both of them on this Argand diagram. Let's multiply these out. We 5 ones are 5. We 5 times 3i is 15i. Then we lift 2i by 1, which is 2i. 15i plus 2i is 17i. We multiply 2i by 3i to get 6i squared, but I squared is minus 1, so that's plus 6 by minus 1, which is minus 6. So we can write this as minus 1 plus 17i. Here is the complex number minus 1 plus 17i. Now, I haven't drawn this to scale, but it doesn't matter. I just want to show you what the connection is between multiplying complex numbers and the moduli and angles, theta, that these angles make with the positive real axis. So basically I want to look at the polar forms of these two complex numbers and how they relate to the polar form of this number here. So we're going to be looking at R1, which is the modulus of 5 plus 2i, R2, which is the modulus of 1 plus 3i, and I can call this modulus R3, which is the modulus of minus 1 plus 17i, and angles theta 1, which is the argument of this complex number, theta 2, which is the argument of this one here, and theta 3, which is the argument of the product of the two complex numbers. In the previous video, we saw how to convert complex number in rectangular form to polar form. So we're going to start by looking at 5 plus 2i. Now, the modulus of 5 plus 2i is root 5 squared plus 2 squared. That's root 25 plus 4, or root 29. Now what is theta 1? That's the argument of 5 plus 2i. Well, we know that the tan of theta 1 is the side opposite theta 1 in this right angle triangle, which has a length of 2, and the side adjacent, which is 5. So the tan of theta 1 is 2/5. So theta 1 is inverse tan of 2/5, which is 21.8 degrees. So we can fill that in here. We're really interested in the general situation. You know, this is R1 cos theta 1 plus I times sine of theta 1. Now here I have converted the other two complex numbers into polar form. For example, to convert 1 plus 3i into polar form, we need R2, which is the distance of 1 plus 3i to the origin. So we just use Pythagoras' theorem. The sides of this right angle triangle are 1 and 3. So we have the square root of 1 squared plus 3 squared, which is the square root of 10. And to get angle theta 2, we just use the fact that the tan of theta 2 is opposite over adjacent in this right angle triangle. So it's 3 over 1, which is 3. So the tan of theta 2 is 3. And if you work that out, you will get theta 2 equals 71.57 degrees. Now, things are a little bit more complicated for this complex number minus 1 plus 17i. R3 is straightforward. We just use Pythagoras' theorem. Again, we have a right angle triangle here. So this side is 17, this side is 1. And we get the square root of 17 squared plus 1 squared. To two decimal places, that is 17.03. Now what about theta 3? You can see that theta 3 is an obtuse angle. It's an angle between 90 degrees and 180 degrees. How do we find that angle? Well, you could start by finding this angle in here. So in this right angle triangle, you can see that the tan of A is the side opposite A, which is 17 units long, divided by the side adjacent A, which is 1 unit long. And you could work out angle A by getting inverse tan of 17. You would get 86.63 degrees for angle A. Then to find angle theta 3, we just subtract this angle from 180 degrees and you will get 93.37 degrees. So I've rounded to 2 decimal places here. Now notice something interesting here. We're multiplying these two complex numbers together to get this complex number, minus 1 plus 17i. If we add the argument of 5 plus 2i, which is 21.8 degrees, onto the argument of 1 plus 3i, which is 71.57 degrees, we will get the argument of minus 1 plus 17i, which is 93.37 degrees. So this is a very interesting fact. In words, we could say that the argument of the product of two complex numbers, which is theta 3, is the sum of the arguments of the two complex numbers, that is theta 1 plus theta 2. Now let's look at the moduli of 5 plus 2i and 1 plus 3i. That's root 29 and root 10. If we take root 29 and multiply it by root 10, we get 17.02, or well, 17.03 to 2 decimal places. So you can see that if we multiply the moduli of our two complex numbers, we get the modulus of the product of the two complex numbers. So R3 is R1 multiplied by R2. So when our complex numbers are in polar form, it's very easy to multiply the two complex numbers. We just multiply R1 by R2 to get R3, and we add theta 1 onto theta 2 to get theta 3, the argument of the product of the complex numbers. We could leave it in polar form, or we could easily convert to Cartesian form. Just go to your calculator, multiply R3 by cos of theta 3, and you get the real part of this complex number. Multiply R3 by sine of theta 3, and you get the imaginary part of the product of the two complex numbers. So these relations are true for just this one example. It doesn't constitute a proof, of course, but it certainly looks plausible. Now let's look at a proof for any two complex numbers, which I'm calling Z1 and Z2. So we're given that complex number Z1 is R1 times cos theta 1 plus I sine theta 1. So the modulus of Z1 is R1. The argument of Z1, often written ARG for short, is theta 1. Z2 is any other complex number. Its argument is theta 2, its modulus is R2. So we want to prove that Z1 multiplied by Z2 is got by multiplying the moduli of the two complex numbers, and the argument of the product is the sum of the arguments of Z1 and Z2. Here's the proof. We want to multiply Z1 by Z2. You can put a dot in here to indicate multiplication if you want. So this complex number is Z1 and we're multiplying by Z2. Of course we can take the R's together, so we get R1 times R2. And then we're left to multiply cos theta 1 plus I sine theta 1 by cos theta 2 plus I sine theta 2. Cos theta 1 by cos theta 2, we just write down. We have to multiply cos theta 1 by I sine theta 2. Now we go to the next term, which is I sine theta 1. We multiply that by cos theta 2. Finally, we multiply I sine theta 1 by I sine theta 2. Now that's going to give us I squared sine theta 1 sine theta 2. But since I squared, of course, is minus 1, we're going to get minus sine theta 1 times sine of theta 2. The next thing that we do is gather the terms that do not involve I together. So this term here and this term here, put them together, they're put together here. And then get the terms that do involve I, which is this term here. This part I've actually written down first, and this part here is written over here. Then we use trigonometric identities for compound angles. We realize that all of this expression here has the form cos A cos B minus sine A sine B, where A is equal to theta 1 and B is equal to theta 2. And we can replace all of this with cos A plus B. So this is the identity that we're going to use. So all of this thing here can be replaced with cos of A plus B, which is theta 1 plus theta 2. Now we'll get another identity for the imaginary part. This expression here has the form sine A cos B plus cos A sine B, where A is theta 1 and B is theta 2. So we can write sine A cos B plus cos A sine B as sine of A plus B. So we can write all of this thing here as sine of theta 1 plus theta 2.